Hey, third grade, it's Mrs. Seals back for our next science lab. So for the next couple weeks, we're going to be talking about something called energy, and we are going to start that out today by talking about sound energy. So your target says I can explore different forms of energy, including sound, in everyday life. So hopefully you'll remember from second grade, energy is the ability to cause change or do work. In third grade, we're going to be learning about 4 forms of energy. We're going to be learning about sound, light, mechanical, and thermal energy, which is another word for heat. Previously in kindergarten, first and second grade, you have learned about sound, light, and thermal. However, this year we're adding a 4th one called mechanical. So this week we're focusing on sound energy. Sound energy is a form of energy that is produced by vibrations. Hopefully you remember that word vibrations. A vibration is when something moves back and forth quickly. So if you put your hands on your throat and talk or go, ah, hopefully you can feel the vibration. You feel something moving. Those are your vocal cords. And when you talk or sing or hum or make a noise, they vibrate. They move back and forth very, very quickly. And that's what creates the different sounds. So another word that we need to talk about when we are discussing sound is this word pitch. And pitch is how high or how low a sound is. So it doesn't have to do with loud or quiet. That's another word called volume. But pitch means high or low. Fast vibrations cause high-pitched sounds. Slow vibrations cause lower pitch sounds. So I'm going to show you an example here really quick. I'll stop sharing and then I'll come back. I have these right here. These are called tuning forks. And they're not like forks that you eat with. These are something that singers or musicians or people who play instruments use to tune to the correct pitch. The big tuning fork is going to vibrate slower and make a much lower pitch sound. The small tuning fork is going to vibrate much faster and make a higher pitch sound. So I'll show you what these sound like. So here's the low pitch sound. And here's the high pitch sound. Are you ready? Hopefully you can hear that on the video. I'm not too sure. But so notice that the lower pitch, the bigger the tuning fork, the slower the slower the vibrations and the lower the pitch. The smaller the tuning fork, the faster the vibrations and the higher the pitch. All right, so let's go back to our PowerPoint. How is sound used in our everyday lives? So I would like for you to pause the video and talk to a grown-up or whoever you're with and see if you can come up with some reasons why sound is important to our lives, how we use it every day, all those sorts of things. And when you're ready, come back to this video. Here are some things I came up with. These are certainly not all, these are just some. We use sound when we listen to music. We are using sound energy. When we are listening to our teacher talk in class, we're using sound energy. When we hear birds singing. When we hear a car beep its horn. When we are watching TV. And when we're talking to our friends or classmates or you know, other people that we communicate with on a daily basis. All of these instances involve sound energy, and they involve vibrations being created and moving through the air into our eardrum, because that's how we're able to hear. As I'm talking, my vocal cords are vibrating and they're pushing the air and the sound wave out of my mouth, which is traveling through the air into your ear, and that hits your eardrum, and then another vibration happens, and that's how we are able to hear sounds. So today we're going to do an experiment to see if sound travels better through solids or gases. Now, if you are at home, you're not going to be able to do this unless you make these objects, which they're pretty easy. It wouldn't be hard to make these. But before I show you how to make them, if you want to make them, I'd like for you to make a hypothesis. Do you think that sound travels better through solids or gases? Go ahead, you can pause the video, share your hypothesis with someone, and then when you're ready, come back. So, to explore sound through a solid, I have these are called paper cup headphones. If you would like to make these at home, all you need are 2 paper cups, a piece of yarn, and 2 paper clips. So what you need to do is poke a hole in the bottom of each paper cup, tie the paper clips onto the ends of the yarn, and just run it through there. So the way this works, and you have to have a partner, which I don't have, so I'm not going to actually be able to do this, but I'll show you how it works. My partner and I are going to talk to each other through the paperclip headphones. So my partner would hold this end to their ear, and I would talk through this end, and they would be able to hear me. I wonder if, no, that doesn't work. So the way that this works is, did you notice how I was pulling the string tight? In order for this to work, there has to be a vibration. So when I talk into this end, my voice causes the paper clip in there to vibrate, which causes the yarn to vibrate, which causes the paper clip on the other side in the other cup to vibrate. And that's how my partner is going to be able to hear me. So, and in order for those vibrations to happen, this has to be pulled tight. Do you see how this is pulled tight? If it's loose and there's slack in the yarn, it's not going to work because it's not going to vibrate. It has to be pulled tight so that there can be a vibration, okay? So that's one way you can explore sound and see how sound travels through a solid. This is a solid, okay? The other way that you can explore sound and to see how sound travels through a gas is by simply blowing up a balloon. When you blow up a balloon, the balloon is filled with a gas, which is the air that you breathed out, right? So the way you would explore this is I would put my mouth close to it, not on it, and as I talk, my voice causes the balloon to vibrate and send the sound waves through, and then my partner would hold it up to their ear so they can hear what I'm saying. Okay, so that's how we can explore the way sound travels through gases. So sound is traveling through a solid, sound is traveling through a gas. So hopefully after you do this experiment, here's what I found out. I found that sound travels better through gases. All day long, when you are listening to your teacher, when you are watching TV, when you are talking to a friend or a parent, sound is traveling through a gas because there's gas all around us, right? All the air around me is a gas. Right now, as I'm talking to you, my sound waves are traveling through a gas into my computer, you know, so that to create this video. When sound travels through a solid, like this string, the solid absorbs or stops a lot of the sound waves. Think about your door. Think about if you are in your bedroom at home and there's a loud noise maybe out in the hallway or the living room and you don't want to listen to it because you're trying to sleep, so you close your door. What happens? The sound gets quieter. You're right. It doesn't completely stop all the way, but the reason it gets quieter is because your door is stopping or blocking or absorbing many of those sound waves and not letting them pass through and into your ears. So sound does travel through solids. However, it travels much easier through gases. because there is nothing to stop it or block it or absorb it. Okay. There are other ways you can explore sound at home. I would love to see if you make the paper cup headphones or do the balloon activity. You're welcome to take a picture of yourself doing these activities and email it to me. My email address again is amanda.seals@killeenisd.org. Please remember that Science Lab is just optional. This is not for a grade. However, there is a short quiz about sound energy after this video. I would love for you to try your best and take it so I can see what you know about sound energy. All right, I hope that you had fun, and I will talk to you next week. Bye, guys.